Science Center. Since we are all doing the seminar remotely and to avoid any additional distractions, please do mute your audio and turn off your video feed during the talk. And as always, we ask that you keep your questions till the end of the seminar, or feel free to type them into the chat to be read by one of our seminar coordinators after the talk. This is the final seminar of the 2022 Groundfish Seminar Series, which is hosted by the Groundfish Assessment Program at the Alaska Fisheries Science Center. Thank you so much to all of our speakers and attendees for another successful seminar series. And I'm going to turn over the stage to Stan Kotwicki, who will be introducing our final speaker today. Take it away, Stan.
Thank you, Sarah. And first I want to thank you, Maciej Tomczak, for making it possible to listen to his talk. I'm really looking forward to it. Maciej is, over the history of the Groundfish seminars, as far as I know, Maciej is only the second person from Poland, originally from Poland, who is presenting. The first person, it was me. And Maciej received his master's degree and his PhD in Gdańsk University, and also my alma mater, from Institute of Oceanology. And Maciej also worked at the DTU in Denmark, DTU Aqua in Denmark, and Baltic Nest Institute at Stockholm University, and currently he's employed by the Institute of Aquatic Resources at Swedish Agriculture University. Maciej research focuses mostly on food web analysis modeling, with special focus on Baltic Sea and fisheries management related questions. After reviewing his publication list, I would also add that his work focuses on high-level changes in ecosystem, either caused by climate change or by anthropogenic influences. But he also works, and he's no stranger to work on more applied science, which includes stock assessments and fisheries management. So he has done a really wide variety of research and tackling the management issues as well. Maciej is a member of many ICES working group with special focus on the Baltic Sea, and I'm really excited to hear more about the Baltic Sea. Some interesting facts about him: he's father of two, his kids are 5 and 10, I just found out, and he's fan of Star Wars and fan of any activities related to fish. And with that, I would like to turn into Maciej for his talk. Thank you.
Thank you, Stan, for such a fantastic introduction. And of course, thank you so much for giving me a chance to talk to you and for the invitation. Today, I will be talking about the state structure and regulatory drivers at the Baltic Sea. This work being done together with colleagues from Sweden, Denmark, Germany, and Finland, because as you know, the Baltic Sea is surrounded by many different countries. So doing this on a single data set is basically impossible. Yes, there were some technical problems. Today I will be talking about the Baltic Sea, and I will follow such a point. Like, first I will talk about the Baltic characteristics, a few words about the current ecosystem dynamic, what we know, what is available from data, and then we ask the question: is it the same sea as 100 years ago? Then that will be our, so to say, research question. Then we talk about the material and methods, data, and different statistics, go to the results and interpretation, and then I try to answer the question to see if we're talking about the same sea or this is completely different ecosystem. because we are quite far from each other physically, these two yellow points, so the distance is quite substantial, I can say. I would like to give you a few words about the Baltic Sea. So the Baltic Sea is the semi-enclosed sea in the North Central Europe, between the Central Europe, East Europe, and Scandinavia, with very narrow connection to the North Sea and to the ocean. That's, of course, making this sea quite special. Because of this very narrow connection through the Danish stairs, I will try to here. The mixing of the water between the Baltic Sea and the North Sea is rather limited. That's of course giving us a special condition on the Baltic Sea. So the Baltic Sea is called sometimes the Sea of Gradients. We have horizontal gradients of the salinity between the fully saline or almost fully saline waters at the southwest, almost fresh water of the northeast. So then this is the one gradient. The other gradient is the vertical gradient, because the saline and oxygenated waters going through the Danish stairs and propagate to the central Baltic and to the Baltic, and because of high salinity, is deposited. It's basically in the bottom layers, and because of the high inflows of the fresh waters, so a lot of rivers going into the Baltic, we have a stratification. One of Baltic properties is extensive hypoxic areas. Here is a condition from the 2015. You can see that anoxic and hypoxic areas are taking substantial amount of bottom as dead bottoms and not oxygenated water. So it's that of course is because of the eutrophication, which causing the deposition of the organic matter, and then waters are not mixing and causing the hypoxic areas. So in this study, we will focus not on the entire Baltic Sea, because as you saw, because of the gradients, it will be quite a lot of differences. But we will look at so-called Central Baltic Sea, so the main water body of the Baltic Sea, where the main processes occur and main biomasses of the main fish stocks are located. So then we can ask, is the Baltic the same sea as 100 years ago? From the perspective of the sea, the 100 years is like one day. It's practically nothing. But even from the perspective of the ecosystem dynamic, it's not that long time. But what happened at the Baltic Sea? First, I would like to also give you a bit about the current ecosystem dynamic. In the Baltic, we have three main fish species, because Baltic ecosystem is a relatively simple ecosystem. We don't have a huge biodiversity as, for example, at the open ocean, because of the brackish waters, because the salinity. So just enough to say that 80% of the entire fish biomass are the three fish species: cod, sprat, and herring. The main feedback loop and one of the main ecosystem dynamic part is interaction between cod, sprat, and copepod pseudocalanus. That dynamic been described by Christian Mellman in one of his papers, but that's not everything. Yes. Of course, we have other conditions affecting this interactions and the stock dynamics. One of this is, of course, fishing pressure. That's well known. And something which we called in the Baltic reproductive volume. This is the volume of water where the cod can spawn and the eggs are successfully developed. Is determined by the amount of oxygen and salinity. That, of course, as well, affecting the other part of the ecosystem, and climate change affecting the other part of the ecosystem. Because sprat mainly feeds on the smaller copepod called Acarcia and Temora, and also the climate affects the copepods, and sprat in particular. So then you know how it more or less working. So Christian Mellman and his colleagues describe the ecological regime shift in the Baltic between the 1970s and 2005, and the transitional period between one regime to the another appear in the end of 80s and beginning of 90s. So first original ecosystem, we call it cod-dominated state, and reorganized ecosystem is a sprat-dominated state. You can see a different interaction strength between the components, between cod, sprat, Pseudocalanus, and Acarcia, and also different regulatory drivers. In a cod-dominated state, there was a lot of cod controlling sprat. Sprat have a very little interaction with the Pseudocalanus, which is the key copepod for the development of the Baltic cod, because it's a key food item for the cod larvae. After the regime shift, we call sprat-dominated period. The sprat is dominated biomass. Cod is relatively low in the Baltic right now. Right now it's almost collapsed, but this is also one of the reasons. And the cod compete with the cod larvae for Pseudocalanus. At the same time, fishing mortality is putting a high pressure on cod. Of course, because of the climate change, the Acarcia start to support significantly the sprat feeding. So that's what we know, what happened between the 1974 and 2005. So what happened next? Well, we have number of information. What was happened in the past? So if we look at the if we look at the period analyzed by Mellman in his paper, the hydrography showing us that in the beginning, in the cod-dominated period, we have a relatively good oxygen, and then some hypoxic areas start to appear in a high frequency. At the same time, salinity been high at the beginning of the time series, and then drop, and then increase again. That's very well correlated with the described regime shift. But we would like to know about the past of the Baltic Sea. The situation been a bit different, looking only in the hydrology. Then eutrophication. Right now, if we look at the period analyzed by Mellman, that was between 1974 and 2005, the biomass of the phytoplankton increased during this time significantly. So we can say we have a high eutrophication. Baltic is eutrophicated area. Nutrients been on the already high level. If we analyze the same data in the past, we see that the eutrophication was not that much the issue. Also, the catches, catch composition, if we go into the past, been completely different. In a cod-dominated period, cod dominated in the catches. Then sprat, but previously that was herring and even flatfish at the 1930s. So it means that can suggest, okay, we can expect some different ecosystem dynamic. So cod-dominated period is really some kind of extraordinary state, or we can say yes, because it was very high and then very low. But looking in the past, the cod biomass was not that high anymore. So what we did, we collect a number of reconstructed data. Some of this data collected from already published work, some of the data from reconstructed by ourselves, like cod and sprat. It's an effect of the work by Margit Eero in the HMAP project. The biomass of the phytoplankton, and phytoplankton is a reconstruction using the biogeochemical models. Reconstruction of the zooplankton and flatfishes are using also different models. And the same with the benthos and seals. The most important is with this data that all of those data been validated with the observed historical biomasses and show very good match with the observed data and trend. So we can say, yes, we work with the reconstructed data. However, this is the best available knowledge about the past we have right now. Similarly, with the environmental data, here we use of the reconstructed of the biogeochemical model, which reconstructed number of forcing, like oxygen, salinity, or temperature. But again, we have a lot of historical measurements to validate. So at the end, where we put all of this data together, we end up with the 15 time series of biotic variables and 16 time series of drivers as nutrients, salinity, oxygen, temperature, hypoxic areas, cod reproductive volume, but also as drivers, we use the fish mortality and the seals abundance. Why seals not only biotic? Is because we know already that seals in the Baltic collapsed because of the hunting and pollutions. So we rather use the seals as a top-down pressure on fish. Then, what kind of methods we use to analyze those data? So when we compile this data set, and we try to compile this data set to be as close as possible to data set prepared by Mellman et al. From 2009. Of course, there are differences because we have a benthic data here and flatfishes, but we use the same principle to choose the time series, to avoid the cross correlations between the variables. Then we use the principal component analysis to see the relationship between the time series, and then to find the time of the breakpoints, we use the two statistical methods. It's a sequential t-test on mean and the BCP, so Bayesian change point, and applied to the PC1 and PC2 scores time series. To find out the main drivers, we use GAM models and test number of combination of the GAM models to find what is behind the data and find the patterns in the drivers for our biological time series. We also repeat this analysis for a subset of data where we found the breakpoints. So, how the dynamic of the ecosystem look like based on the PCA? The PC1 showing stable increase, and this trend is mainly associated with the variables related to the productivity of the system. Zooplankton, phytoplankton, also benthos. PC2 scores are related to the dynamic of the sprat, cod, and the pseudocalanus. So this is what we know. And the drop represent the shift by Mellman in the end of 80s, beginning of 90s. So if we apply the breakpoints, we definitely found the shift in the PC1 in the 70s. But because of the PC1 is related to the productivity variables, that it means that something happened in this, something happened with the productivity. If we look at the other breakpoints, significant breakpoints, we found that we found the shift in the 1930s, then shift around the 70s, and then end of 80s, beginning of 90s. So with the shift end of 80s, beginning of 90s is matching pretty well the work done by Mellman on the observed data. So we can say we are quite good here. What means the other shifts? Yes. Then it means that we can split the period between the 1925 and 2005 in two separate periods based on the system productivity. And then we would like to see if those periods are very different, if there are differences in the relationship between the analyzed variables, and if we have similar dynamic. And then we found that they are not exactly matching the same. They are different relationships, especially in the historical period. So the first row between the 1905 and 1972, where we have a different position in loadings of flounder, opposite to the Bentos benthic variable. Of course, the interaction between the sprat, cod, and pseudocalanus are pretty much the same. If we look at the data subset between the 1973 and 2005, we have pretty much the same pictures and in the Mellman paper, with the regime shift in the end of 80s, beginning of 90s, and the dominated dynamic between the cod, sprat, pseudocalanus. But here, flounder is following the benthic variable. What can tell us about the ecosystem? It, of course, some changes in the structure. But then we also did the analysis of the drivers. And we apply the GAM models, and the best significant GAM models give us some information about the drivers, regulatory drivers for a given component. And then in the primary production for both periods, the historical and the present period, of course, nutrients like phosphorus and temperature play a major role. That's quite obvious. In a historical period, for the benthic variables like Macoma baltica, for example, there was a productivity and temperature play a role. And for flounder biomass, that was sea surface, that was basically salinity and temperature and some oxygen in the deeper water. If we go to the present period and analyze the same data set, the GAM model shows us that for the primary production, the productivity is, of course, the same variables regulating this. But for the benthic related variables like Macoma suspension feeders, the hypoxic area and oxygen start to play a role and appearing in practically every other variable as a significant driver, both for cod and for flounder. For sprat is because it's carrying the signal of the cod reproduction. So we can see that here the oxygen becoming a player. And here, this is the story of the Baltic Sea. We think can describe based on our analysis. So first of all, we found that the ecosystem shift from the low productive state with the oxic conditions to the high productive state with the hypoxic condition. Then, during the low productive and oxic state, we distinguish two periods. The first is a flounder peak, because the flounder peak is characterized by the very high flounder biomass, never observed later in a history. And then, of course, interaction between the flounder, benthos changed. At the same time, biomass of the sprat and cod was not that high. However, it was very well supported by the feeding condition on Pseudocalanus, so the big copepod. Then, with the increasing system productivity, that's why the box is a bit bigger, the ecosystem reached something which we called reference state, where more or less all of the interactions been in balance, the same biomasses. This period is characterized by the relatively stable biomass or components without any particular blooming and relatively constant anthropogenic pressure as well. And then we observed kind of boost of productivity. There was a shift from to productive phase, and then the biomass of the ecosystem increased significantly, and the trophic condition became a very good and supported very well by primary production, still with the high salinity and good oxygen condition. Then the primary production support not only pelagic food web, but also very well benthic food web. And then we have, of course, evidence in the data, of course, and cod been feeding on the benthos, still putting the top-down pressure on sprat. That's, of course, have a confirmation in the data and the diet composition change and the diet composition, because in this period between the 70s and 90s, cod diet composition composed from two different parts. That was a pelagic part, it means sprat and herring, but also 50% of the benthic invertebrates. Of course, at the same time, we experienced the collapse of seals. So there was no seals because of the pollution and hunting. Because of the very high salinity during this time and still good oxygen, cod reproduce very well, been supported by the Pseudocalanus, and compete about the benthic resources with flounder. Then we have the discontinuous regime shift sensu-Mellmann, and ecosystem turn into the sprat-dominated period. And during this period, some interactions change significantly, especially those connected with the cod and benthos and seals and fish as well. During this time, it's a time of the very low seals biomass, which are a bit higher, well, even I can say much higher right now. But in 2005, the cod been very low. At the same time, cod stock almost collapsed. Sprat is very well supported through the pelagic food chain from primary production through the small copepods, and because of the low salinity, Pseudocalanus is not that much available for the cod larvae. So the feeding condition of the cod larvae are not great. And because of the high sprat biomass, the feedback loop, sprat is competing with the cod larvae for the resources. Then we also found the confirmation in the data here, because after the regime shift, cod switched almost exclusively for the pelagic feeding, and this is the main predator on sprat and herring in the Baltic Sea. So, and of course, because of the extensive, which I have to add, the extensive hypoxia do not decrease the biomass of the benthic resources available for cod and potentially flounder. So that's more or less the entire story of the Baltic Sea. So if we would like to if we would like to answer our question at the very beginning, is it the same sea? No, it's not the same ecosystem. It's a completely different ecosystem which switched from oligotrophic to eutrophic condition with the regime shift in a trophic state. We have a different trophic pathways supporting the system more from the pelagic pathways, not the benthic pathways. In a historical period, there was probably the much stronger pelagic benthic coupling because of the benthic resources more available. And we think there was a change in the main controlling drivers from salinity to oxygen. So because of the hypoxic extensive hypoxic areas. Also, the eutrophic state being a foundation, a basis for the regime shift in the end of 80s, beginning of 90s. So first we had this shift in a trophic state, and then there was the foundation for the regime shift from the cod to sprat dominated period. And because of that, we would like to highlight that eutrophication in the Baltic had a much broader impact than direct and indirect than only, for example, on productivity and only on the phytoplankton. Because of high eutrophication, the ecosystem changed significantly. But of course, during this talk, I miss a lot of details. I miss a lot of data description and method description. But if you would like to know more about the details and methods we use and models which are behind the reconstructed data and have also the metadata for the reconstructed data, all of this is available in our paper, which we published in the limnology on oceanography last year. So thank you, and I'm happy for a questions.
Thank you, Maciej. That was a really great talk. If anyone has any questions, feel free to unmute yourself. You can turn your camera on too and ask questions directly to Maciej, or you can type any questions you have into the chat as well. Looks like Stan has his hand raised. Go ahead, Stan. Oh, you're muted, Stan, sorry.
Thank you, Maciej. It was great talk, really very interesting. I have a few questions, but let me start with maybe the most important for this audience is, to me, my first impression after your talk is, there's lots of data going to it. It's very complex project, and I think your story is really convincing. So how do you take on a project like this, and how do you make it happen, and how do you take it from the beginning to the conclusion like this? It must be pretty daunting task.
Practically, it took a couple of years. The most time consuming part was actually the data collection, where I bring a number of researchers and engage number of colleagues working on a similar tasks, and that was the bringing data together took couple of years, because in one institute they did the reconstructions of the biogeochemistry, and the other was the reconstruction of the fish, and also the completely other project deal with the reconstruction of the benthic data. So when the data been ready, and we somehow try to find the so to say the final data set we would like to work with, then it was not that super difficult, because the methods applied here, been quite well developed for the integrated ecosystem assessment in the ICES integrated ecosystem assessment framework. And this particular methods, we call it integrated trend analysis, have been well published couple of times and developed under the ICES integrated assessment of the Baltic Sea. So the analysis and the conclusion process, so to say, the scientific process behind it was not that complicated. The most difficult was actually to get the data. And have to say that there was no particular one project supporting this activity. There was a number of projects supporting different people. So we can call it the synthesis in that respect.
Great, thank you. I have more questions, but if there are other people who have questions, maybe we can reach out to them.
Doesn't look like anyone else has their hand raised at this moment, so let's say you can go for it, Stan.
To me, I wonder if when you were reconstructing the data and you reconstructed the time series of the biomass or abundance estimates, like 100 years back. I know in the recent history, we have fisheries independent surveys, but before, actually, I don't even know when the fisheries independent survey started in the Baltic Sea. But how can you explain to us in the simple words, how you can reconstruct the fish biomass if you don't have actually fishery independent data?
Yes, so there are a couple of methods. I think my colleague from DTU Aqua, Margit Ero, is a very high-level specialist, is doing these things. But as far as I know, there are two ways of doing this. The first, especially for cod, Margit spent years of her PhD in archives of different institutes around the Baltic and in Germany, and around the Baltic in Germany as well as one of the main sources, in the libraries, digitalizing the fishery dependent data like catches, and also the, so to say, fishery independent observation from historical sources, right? Which allow to verify the stock dynamics and verify, for example, the fishing effort and catches. So this is the one method. And then Margit apply, and also also the verify assumed age structure, because one of the methods used for the cod was actually the VPA. So that was the reconstruction using the VPA. The other methods used here is the reconstruction based on the surplus production. And then when we had the models reconstructed with surplus production, take into account also density dependence, we can reconstruct the model back knowing the historical catches. And again, that was a years of reconstructing the catches itself, but also fisheries independent historical information. I don't want to go here in the very neat details and nitty-gritty, because that's, I think Margit can explain it best. But I know that also some surveys and old biological samples like eggs production, eggs abundance been took into account for the reconstruction.
Great, thanks. It's very helpful.
So that was very much work more on history than biology itself, but as an end product, that's a historical time series. And if you know exactly, there are papers by Margit Ero published, I think one in the Canadian Journal of Fisheries Science, the other I don't remember. That might be ICES Journal of Marine Science, but both of them are published. And how the flounder is reconstructed is supplementary material to our papers.
Okay.
Great. It looks like we have a question in the chat from Jeff Tingley. He says, great seminar, thanks. This appears to be a complex study, but the ecosystem is relatively simple. Do you consider such approaches would be equally successful in a more complex ecosystem with multiple fish and other species?
Yes and no. The answer is not easy because this method been applied by a number of ICES working groups in many different ecosystems. We try in the Mediterranean and it was published successfully. That was applied at the North Sea and it was published successfully. So yes, in a more complex ecosystem, it will be definitely working fine. I also apply for the Namibian coast and Namibian currents in Africa, and yes, it's working fine. However, right now, since we of course start our investigation and we start our approach, the methods for this kind of analysis develop significantly. That's thanks to the Saskia Otto and Benjamin Plaquet. They have a series of fantastic workshops developing methods for the integrated ecosystem analysis like this. So I really encourage you. This is very basic setup, so to say. This is a very, very basic setup of methods. The methods are better. Some methods could be even better suitable for this kind of analysis in the ecosystem, which are more complex and have a more components.
Great. Stan, do you have any other questions? Your hand still raised. I'm not sure if that was new or.
Yeah, I do if there's nobody else.
Does anyone else have questions? I don't see anyone else's hand raised. So.
Yeah, so another thing that I'm wondering, I think this hypoxia, it's very interesting, and over the years, and of course when I was studying in Poland, I remember we were talking about this and those hypoxic areas increasing in the Baltic Sea. What's your feeling? What's contributing to hypoxia more? Is it the anthropogenic influence mostly, or less flow from the North Sea, or and also in addition to it, if the hypoxic areas are increasing, it kind of, in my mind, it makes sense that the space for at least flatfish and the benthic organism is decreasing. So and the pelagic environment is maybe at that point underutilized. So that's why this transition happened. Can you comment on those two things?
Yes. So they are equally important because of the as you know, the catchment area for the Baltic Sea is around 40 million people, 80 million people, so kind of a lot, living in the 8 countries. If we count the Norway, that will be 9 countries, and especially the southeast is very rural and agriculture, so a lot of nutrients going from there. So historically, the anthropogenic nutrients input is the thing which makes the eutrophication and contribute to the hypoxia. Of course, we cannot neglect climate change because the major inflows from the North Sea, which carrying the saline and oxygenated water, are less frequent right now. So that's have to the overlap of these two things, of course, contribute to the hypoxia. I'm not a biochemical specialist, but because of the high phosphorus loads historically, a lot of phosphorus have been actually stored in the Baltic sediment, and in the hypoxic conditions, the the phosphorus is made available again through the system. So it's so-called internal load and internal leaking of the already deposited the deposited phosphorus, and that's of course making the eutrophication and faster and hypoxic area even more severe. I don't know if I answered.
Oh, sorry.
Yes, you did. But can you comment about like the decrease of the benthic?
Oh, yes, sure. Yes, the theory is that that's of course still ongoing discussion, that the benthic resources decrease. Some researchers showing that they are increased, but the true, so to say, is between. So it means that yes, the deep water resources below halocline are not available for the cod and flounder anymore in that extent it was historically. However, the benthic resources above halocline, where the oxygen is still fine, increase because they increase the primary production. So that's the issue. And of course, change in the species structure and the benthic structure also affecting the fish eating the fish eating the benthic resources.
Makes sense. Thank you.
We have one more question in the chat from Jim Uphoff. He asks, has this analysis been integrated into fisheries management?
Oh, good question. No, no, been not available, been not integrated, because right now in the European Union framework, we are really struggling to get the integrated ecosystem assessment and ecosystem-based fisheries management. We still in the fisheries management pretty much single species and without any practically without any ecosystem consideration. I currently running the project which supposed to develop the roadmap how to make the ICES advice supported by the ecosystem information. So ecosystem-based ICES advice. We know about these changes, but no, this kind of informations are not in the fisheries management. They are way more took into account into the environmental management, because in European framework we have a marine strategy framework directive, and one of the descriptors in the framework directive are related to the food web dynamic, and this kind of information, of course, fit into the descriptor 4 and can support the development of the food web indicators. But with the fisheries is a really problem. That's true. Just last week, we had a seminar also with the Sean Lucy discussing the integrated ecosystem assessment program in US. So we are communicating with your colleagues.
Yeah, I think that's great. I think, you know, also your work is an example of really of collaboration across so many different countries and collecting data from different sources. And I think in the US, we still have lots of work to do to make it easier for us to collaborate with, you know, Canada, Mexico. I'm not mentioning Russia here, which is really, really difficult to collaborate, but we share ecosystems with them, and we need to, I think we can learn a lot from European experience.
Oh, this is the same. We're learning a lot from the US experience, especially regarding the ecosystem-based fisheries management, because this is where we're really lagging behind.
That's great. That's great. So yeah, so we need to be helping each other.
Maeve Moriarty just put in a comment in the chat. She said mixed fish advice was considered this year for the first time, as far as I know.
Yes, that's true. That's true.
Yep. And Jim just said, no better in Chesapeake Bay.
Yeah,
Does
actually,
anyone-
Chesapeake Bay is one of the interesting area here because late in the 80s there was even program for joint studies of the Chesapeake Bay and the Baltic Sea. I think there is a number of publication by the Swedish researchers, because by characteristic Chesapeake Bay is quite similar to the Baltic Sea. So I know there was some initiatives with the joint studies and comparative analysis.
Does anyone else have any questions for Maciej? Feel free to raise your hand, unmute yourself, ask away.
I had a question, so thank you for a great talk, and I actually work with Sean Lucy, so the question is sort of related to some of that, which is I've read some of your earlier work about using ecopath models and looking at some of the resilience attributes in the Baltic Sea. And my question is, one is, do you still think that the ecosystem is in kind of a more low resilience state? And if so, do you expect further shifts or regime shifts in the future? And two, is there any interest in doing some of kind of extending some of those analyses further back and looking at some of those properties further back in time now that you have all the data together?
Thank you, Sarah, for this question. That was a question I've been waiting for. No, seriously, regarding the regime shift and resilience of the system based on the ecological network analysis, we discussing this seriously because this is the serious issue which might affect management in the future. So the system is, we think that with the new data right now we have since 2005, and I would like to do the modeling of this, do the model exercise on the newest data. We think that the system in the Baltic have a relatively high resilience right now, and it's locked in the Sprat dominated period, and it will be very difficult to push it to the completely different ecosystem. It might jump somewhere into the novelty of the system and reach state which we didn't expect, so to say, right? So it might be basically shift, but something where we don't know, but it will very much depend on the anthropogenic pressure and how we will manage entire ecosystem. It might be that the dynamic will be similar as the Black Sea, that it will turn into the completely pelagic dominated system with the jellyfishes. But on the other hand, it might be if we will manage the fishing pressure and eutrophication in the right way, as some of the other modeling work showing, it might turn for the flounder dominated system, maybe not in that configuration as we had in the 20s, but it could happen that the benthic component again start to dominate. Who knows? It's very much depend on the management. At least we are talking about the 100 years perspective, right? In the future. So we never know. Regarding the reconstructing data back, yes, we planning to do the modeling exercise using the food web model to reconstruct data to the so to say 100, even more 100 years back, and to the medieval ages as well, because we have data about the fisheries catches and catch composition from the medieval ages based on the work done by historians and colleague Rudi Voss from Hans Albrecht University from Kiel. And Rudi have a fantastic, did a fantastic job about the historical catches from the Hanseatic towns around the Baltic. So yes, we're planning this, and the work is ongoing. So I hopefully can give you an update within a year about such a. This is fascinating. I mean, going back in the history in such a, even using the models is really fascinating.
That's so cool. Thank you.
Does anyone else have any questions? Feel free to raise your hand, unmute yourself. All right, I'm seeing no more questions. There's a comment. Thanks for speaking to us from 9 time zones away. Thank you so much, Maciej. This was great.
No problem. Thank you. That was my pleasure.
Very interesting research. And thank you so much for all of the participants that have come to all of the seminars this year. It was a wonderful seminar season, and we really appreciate, everyone gathering and sharing this knowledge together. So thank you. Have a great rest of your day, everyone.
Thank you so much.
Thank you, Maciej.
Thank you, everybody.
Thank you.
Maciej, do you have a few minutes to stay?
Yes, absolutely. Absolutely.
I was just saving the chat. I'm going to stop the recording so you guys can